Hi everyone. In this video, I'll be talking about microcontroller instructions, instruction cycles, and clock speeds, followed by a practical experiment to peek at machine code and observe how these concepts impact on execution time. Before we start, I will try to stay away from the details as much as possible, but let's have a quick refresher on frequency and period. For cyclical thingies such as oscillations, waves, frequency is defined as the number of cycles or vibrations per unit of time. For any given signal, such as these samples here, it's basically the repeating pattern that you will see. And period is the time taken to complete one such cycle, such as this one. Given period of a repeating signal as t, frequency is 1 over t. The standard unit for frequency is hertz, replacing the previous name, cycles per second, but the meaning is exactly the same. So a 1 hertz signal means 1 cycle per second. A 1 kilohertz or its multiples means 1,000 cycles per second. 1 megahertz is a million cycles per second, and 1 gigahertz is 1 billion cycles per second. The standard unit for period is seconds, and some of its multiples are, so 1 second is 1,000 milliseconds, and 1 million microseconds, sometimes written as US2, and that equals 1 billion nanoseconds. And here we have our good old Blinky project from previous videos. We have the micro PIC10F here, and we have a PIC3 hooked up to it. We're gonna program it, and it's also used to power the circuit. And we have an LED that's wired up to the connected to the micro via a 220 ohm current limiting resistor. And I have a bit scope, USB scope here, which is probing the same pin, GP0 pin, that the LED is connected to. And even though we are golfing with a 70-cent silicon here, these concepts apply pretty much to every processor, including your AVRs, ARMs, AMDs, Intels, Apple Silicon, etc., with architectural differences in implementation details. I have our MPLAB IDE open here, which is the Blinky code, is only a single file. On the configuration bits front, we have everything off, and micro is set to run its internal oscillator set at 8 megahertz. And on the main method, we are setting our GP0 as a digital output, and we are looping and toggling it. So let's make this code a little bit simpler to understand what's actually going on the frequency and period front. So instead of toggling it, I'll just set it and clear it implicitly, and then add some delay in between. So with 0, we want it to delay, instead of 1000 millisecond 1 second, I'm just going to put 100 milliseconds here and 100 milliseconds here as well. It's just supposed to be GP0. So when I do that, we have a repeating signal. It goes 0, waits for 100 milliseconds, and then it goes 1, waits for another 100 milliseconds. So, and we have our signal in repeat. Our period is 200 milliseconds, and that, if we divide it to 1 second, divided by 200 milliseconds, or 0.2 seconds, we have signal of 5 hertz. Now we have a very fast blinking LED, which we can see here. We have an LED that's blinking for every 200 milliseconds. And let's see what's on our scope. So the scope I have is a Bitscope Micro USB air quotes scope, but it's more than good enough for the job. So our period, our divisions, the time division set here are to 100 milliseconds. So each division you see here is 100 milliseconds. So this is the end of our cycle, and this is the beginning of our cycle. Okay, so I don't know if you can see it. It's quite tiny, but here you can see our period is at 200 milliseconds, and our frequency is 4.4. Because it's not exact, I can just adjust the stuff a little bit. Yeah, okay, it's close enough. We have like a 226 milliseconds period, and we can also see the frequency at 4.4 hertz, which is close enough. It's really difficult to get that sorted. Put the cursors in right at the beginning and right at the end, and there is also some other stuff going on in the code, which we will talk about later. I think that's good enough. Now let's try to create a faster signal. So we have now 100 milliseconds. What if we go down into the microseconds world? Okay. Now our period becomes 200 microseconds, and that should give us 5 kilohertz, right? Now, if you look at our circuit, the LED is not blinking anymore. Well, it actually is, but it's just too fast for our eyes to see and for the camera to capture. So let's change our divisions to 100 microseconds per div. Now we can see our signal again. Now let's set our, let's see what we have here. Our period is 228 microseconds, close enough. And our frequency is 4.3 kilohertz. Again, it's pretty close enough given the other stuff happening in the code. Let's have a look at our datasheet to understand the performance characteristics of our micro a little bit more. It's a high performance RISC CPU, and RISC here is reduced instruction set computer. CPU is for central processing unit. So the processing unit in this micro has only 33 single word instructions. So where are those instructions? In the MPLAB, what we see here on our main C is just plain old C code, and there is no instructions here. This is just C code. What your compiler does is to convert this C code into instructions that are suitable for the device that we are programming. So if you go to the window and target memory views and choose program memory, you will see those instructions that are programmed to that are supposed to be programmed to the PIC. So if you look at this code, I'm not going to go into the details of the assembly codes, but you have the line number, you have the address, you have the opcode, the machine code, and you have the assembly instruction corresponding to it. It's sort of more human readable. So if we go to, I can recognize the ADCON here. That's for setting the clearing the analog digital control bit. And we have the trace as well, which is being cleared. And the whole action happens in these three lines. So in this one, it's writing one to the W register. And in the next one, where we have this line toggling the bit, it's basically this XOR WF is just XORing the GPIO with whatever is in W and then writing it back. Now, if you go back to our datasheet, there is another very important thing here. All single cycle instructions except for program branches, which are 2 cycles. Program branches are anything that's like go-to statements that causes the program counter to jump to somewhere else in the program. And at the end, it talks about operating speed, which is 500 in nanosecond instruction cycle with 8 megahertz internal clock. Well, 8 megahertz frequency is 125 nanoseconds. But here it's talking about 500 nanoseconds. And why is that? And this happens because the instruction cycle and the clock cycle are different things. Instructions are executed in stages, and each stage is complete in one clock cycle. So these stages are for the PIC microcontrollers are decode, read, execute, and write. So each of these stages are completed in 125 nanoseconds, which is the period for our clock frequency at 8 megahertz. If you look at a similar 8-bit micro ATtiny series, and the datasheet it says up to 12 MIPS, like million instructions per second, throughput at 12 megahertz. So it looks like this micro is able to execute an instruction at every clock cycle, but not really. This is also a 50-cent micro. It has a more modern architecture compared to PICs. It's a very, very powerful micro, but it's not actually executing an instruction at every clock cycle. I'm not going to get into the details of the AVR architecture, but simply what happens is that while the first instruction is proceeding into the next stage, the next instruction just gets into its first stage. So doing that way, there's some sort of parallel execution happening. So if you have all single cycle instructions and no branching in an AVR micro, you can definitely achieve one instruction cycle per one clock cycle. Now let's go back to our code. Now we look at our code, we are toggling, we have go to statement. Okay, let's see what we have on our scope. So yeah, we have still a bit jumpy, so I'm gonna stop that. So after adjusting the cursors, we are looking something close to 4 microseconds for the entire signal. Okay, so let's have a look at our instructions. We have one instruction to move 1 into W register, another instruction to toggle the GP0 pin, and another instruction to loop. So if you look at these instructions, each of them will take 500 nanoseconds except for the go to one, which is going to take 2 instruction cycles, which means this is going to take 1000 nanoseconds. So if you sum them up, looking at the loop point, this instruction is 500 nanoseconds, another 500 nanoseconds, and 1000 nanosecond for the branching instruction. We are looking at 2000 nanoseconds, which is 2 microseconds. So our GP 0 pin will be 0 for 1 microsecond, for 2 microseconds, and then will be 1 for another 2 microseconds. That's why we are looking at 4 microseconds in our scope. So if you look at that, if you move our cursor a little bit further down, we can see our GP0 pin is high for something close to 2 microseconds, and then it's also low for something close to 2 microseconds. And the last bit is that I'm just going to show you some wacky stuff that we can do to make this even faster. So if you notice the code, there's like, again, we are interested in only 3 instructions. So this instruction puts 1 into the W register, and then the next instruction is just applying an XOR with the W instruction to GPIO 0 pin. So, and then our code goes back to address 6, which is again moving the 1 into W register. But we don't need to do that in each loop, so we can do this once. So I'm going to get rid of this loop and replace it with a more hands-on approach. Well, what we have here now is, again, we have this, we are writing 1 to the W register, and then toggling our GPIO with the XOR WF operation. So, and at the end, we had this the end of the program, it will go back to the beginning. So we don't want that. Instead, we want to go back to the previous address, which is address 07. So I'm going to use a special directive called ASM. That's to inject like one line of ASM code into our C code. So this is real wacky stuff, but it's gonna work for this case. So we just write a one-liner assembly instruction there, which will go to address 7. Let's compile our program again and have another look at the program. Now we have the toggling, and then after that we will go back to 7. Okay, so what's going to happen now in our loop is the toggling, and then the branching instruction, and then the toggling again. So the branching instruction is, we know that it's 2 instruction cycles, so it will take 1 microsecond, 1000 nanoseconds, and then the toggling will take 500 nanoseconds. So in total, our loop will be 1500 nanoseconds. Let's program that into our PIC. Okay, and let's have a look at our scope. Turn back on the tracing. Yeah, I'm just going to stop the tracing there, adjust our cursors, and if you look at this on state, you can see that it's 1.7 microseconds, close enough. And what is the frequency here? The period of the whole signal is 3.3 3 microseconds, and that would give us something close to 300 kilohertz. And after that little bit of assembly duct taping, we managed to get it faster. And as far as I know, this is as fast as we can go with this PIC. And that's a wrap. Thanks for watching.